Modern systems architecture often operates on the assumption that measurement is synonymous with reality, that if we can record a data point, we understand the state of the system. Consider a three-dimensional cylinder rotating in space. An observer only sees its two-dimensional shadow, a circle or a square. The sensor captures this, but depth is stripped away. The latent fibers dictating behavior are missing, so algorithms calculating velocity will completely mismatch physical reality. This gap between the true state and the observed record is the hidden state problem. Architectures that treat the available record as the complete state fail to account for the information that is missing from the sensor, leading to control actions that are inadmissible in the physical reality. Optimizing algorithms based on these coarse-grained projections create structural defects because those unseen latent fibers continue to dictate how the system actually moves. Descriptive modeling encounters a specific friction when applied to high-consequence, globally entangled environments. Most current systems rely on unconstrained statistical optimization, predicting future states based on patterns in filtered data. In these models, physical limits are treated as post hoc penalty functions, rules written in software to correct the system after it drifts. An alternative is a framework of governed dynamics. Within this framework, physical laws are encoded as geometric inevitabilities in the mathematical substrate. Designing for these unforgiving domains requires a shift from describing what is occurring to enforcing what is allowed through mathematical governance. The interior of a tokamak fusion reactor is one of the most complex control environments in existence. Because the plasma is a high-energy, high-dimensional entity, sensors can only capture a sparse, partial record of its behavior. This creates a mathematical limit. The true topology of the plasma cannot be perfectly reconstructed from the available sensor arrays. Traditional control systems use standard partial differential equations to model the plasma's flow based on sensor observations. If a calculated move violates a safety boundary, an external penalty pushes it back, creating a chaotic feedback loop along the safe zone's edge. This numerical drift leads to defect accumulation, where small losses in information compound over the duration of the reaction. In fusion, that drift results in a nonlinear tearing event. The plasma loses its symmetry and strikes the inner wall of the containment vessel. Relying on external software penalties to manage a hidden state system allows for micro-violations that eventually result in machine damage. To solve this, the Coh framework replaces standard equations with abstract dissipative Hamiltonian differential algebraic equations, or ADH-DHEs. The structure of this equation is defined by the singular E and Q matrices. These singular matrices allow physical constraints to be represented as inherent algebraic features of the system rather than external additions. This embeds the constraints directly into the geometry of the state space, creating impenetrable topological walls that the system cannot drift through. This geometric structure achieves algebraic closure. Transitions within this space are restricted by the underlying geometry, ensuring the system only moves through valid, predefined paths. Under this paradigm, we do not use rules to punish a violation after it happens. We build a mathematical space where illegal moves are undefined. The absorbing boundary is the exact mechanism that enforces these geometric limits. Through the Moreau sweeping process, any velocity approaching the boundary is projected onto a tangent cone. A reactive force resides in the normal cone, acting to algebraically cancel any component of the velocity pointing toward the wall. The path toward violation is extinguished. This ensures every state change is part of a funded evolution, where every transition is tracked by a thermodynamic ledger. The system operates under a thermodynamic budget, B, which represents the available resources for change. This leads to the velocity level collapse. If a system exhausts its budget, its motion is forced to zero. This occurs because the constraint requiring the budget to remain non-negative and the law governing metabolic spend intersect at exactly zero. At the boundary of resource exhaustion, risk-increasing velocities are algebraically deleted before they can manifest in the physical world. While geometry defines the boundaries of motion, the act of observation creates its own structural challenges through coarse graining. When continuous microphysics are compressed into macroscopic records, information is lost in the projection. The individual paths that disappear during this compression form the hidden fiber of the system. The Oplak's subadditivity law serves as the mathematical safeguard to maintain thermodynamic honesty during this process. Because the observer cannot see the hidden fiber, the model must assume the worst-case dissipation. This ensures that the macroscopic record never artificially invents energy. In this view, irreversibility is an inescapable algebraic requirement of bookkeeping, a method of ensuring that models remain grounded in physical reality. These constraints apply to cognitive architecture as well. Standard AI models often treat reasoning as a transition that incurs no resource cost. Governed metabolic intelligence treats reasoning as a strictly bounded process, where every single step is subject to metabolic limits. Within the Coh framework, every state update must produce a certifiable proof of its own validity. This is formalized as a lean-for contract, which guarantees that a system's risk and resource expenditure remain within modeled boundaries. By integrating algebraic closure, explicit cost, and verifiable receipts, we move from trusting a descriptive flow to verifying a lawful transition.